a boundary V, but let's call the surface S. So S is a closed surface because it contains a three-dimensional region. Now, at any point on the surface, we have a normal vector. That is the outward unit normal vector. And again, the term positive orientation is used, but it has a different meaning in this context. Right. So when you're talking about positive orientation for a closed surface, it means it's pointing out from the solid that it contains. Okay. Now, so suppose you need to compute the surface integral of some vector field over this entire closed surface, which might be quite a pain to do. Imagine if this was not a blob, but say a box. Now a box might seem like a simple thing to compute a surface integral over, but a box has 6 faces and you got to do all 6 individually. So who wants to do that? So it'd be nice if this could be described as another integral that might be easier. A triple integral over the solid that it contains. So to do that, let's do the following and take slices of this solid. So you can think of these as being like latitude lines, if you will. So you're just slicing the solid in whatever way. Then each slice is going to be a surface, and that's going to be contained within a closed curve. So here we're going to have a curve C1, C2, and so forth, bounding a surface S1, S2, and so forth. So you can have a bazillion of these slices. Now, on each slice, you can apply Green's theorem. Which says that the line integral of a vector field around the curve is equal to integral over the surface that it contains of a divergence of a vector field. All right. Now, wait. Oh, sorry. Messed that up. It's not that line integral, it's this line integral. F dotted with a normal vector ds. So, to go along each curve, we have a normal vector to the curve, and if you set up these slices right, the normal to the curve is going to be the same as the normal to the surface at that point. So, because we're pointing in this direction from this curve. So this is what's happening on each slice. So what you can do, now I'm very much waving my hands here, but just to try to give an intuitive idea of where this comes from, there is a proof of a very simple case of this theorem in Stewart that I find intuitively altogether unsatisfying. What happens is if you combine what's happening with each slice, you can think of the thickness of each slice as some very small dz, for instance. Then, you put all this together and you get the integral over the surface of f dotted with the surface's normal vector And that is equal to the triple integral over the solid of a divergence of f. So this is what's happening on each slice. On each slice you're applying Green's theorem, sum them up, times this slice thickness dz, and what you get is this result. This is the divergence theorem. I'll give a full name. The Gauss divergence theorem. But often it's just called the divergence theorem. Actually, I think, well, Stewart calls it the divergence theorem. I believe Marsden calls it just Gauss's theorem. So, a lot of some books call it the Gauss divergence theorem. Those are the names. Pick whichever one you want. Okay. So this is the final vector calculus theorem. So we had the fundamental theorem of line integrals, Green's theorem, Stokes' theorem, which is now erased, and then finally the divergence theorem. All of them relate an integral over a certain region to an integral over a region that's one dimension higher, but involving a derivatives of what you're integrating in the first place. In that sense, all of them are generalizations of the fundamental theorem of calculus, which we're going to explore next week when we talk about differential forms. So, the use of a divergence theorem is this. If this is what you are having to evaluate in the first place, then you might find that by instead considering an integral over the solid that it contains, you might find this integral to be easier. Okay, so let's do one of those. Okay. All right. Now, suppose we have this vector field.
Oh, we need to pass out who wants DVDs Thursday, right?
Oh, yep. X z to the 4. So here's your vector field.
Yeah.
And then the surface is a box, and the vertices are x coordinates are plus or minus 1, y coordinates are plus or minus 2, z coordinates are plus or minus 3. So these are your bounds in x, these are your bounds in y, and then here are your bounds in z. So it's going to be something like so it's not all that thick in x, it's somewhat thicker in y, and it's the largest dimension is along z. Okay, so you want to compute double integral over the surface. The normal component of a vector field by expressing it as a triple integral over the box of its divergence. Now, computing this directly, you could do that, but it's very tedious because you have to do each of the 6 faces separately. Yes?
Did we get a sheet to start these, or when should we do that?
Oh, yeah. Let's see.
For yeah.
Okay, let's pass it around. All right.
Easy one.
Yeah. Okay. So, if you want a DVD, let them know. All right. Because on each of these faces, you're going to have a different normal vector pointing